Hi guys, in this session we want to continue our discussion about machine learning theory, and we want to talk about model selection and also cures of dimensionality. Okay, so these are two important topics in machine learning which we want to talk in this session. Okay, if you remember our example about polynomial curve fitting, there was an optimal degree for polynomial, or actually our model, to estimate the data. Let me again show you the example. Was we have some data with some noise around sine of x, and so these are our training data, and we want to estimate this with a model, with a polynomial. In other words, our model is w0 plus w1x plus w2x power 2 to wm x power m. Okay, so the degree of this polynomial is m. Now we saw that if we have a very high polynomial degree, we will have something like this. And this is not a very good estimation of what we want, because we want our learning model will be something like this. But if we have very high order polynomial, we will end up with something like this, and we call this phenomenon as overfitting. In other words, in overfitting, our model is too complex for our data. We will get a very good performance on our training data. In this case, we will get zero error in least square, because our cost function was the model prediction minus the actual training data square over all the training data. So we will get a perfect this is the cost function. For this complex model, we will get the cost function equal to 0, means that this is the minimum of this function, but we know that this is not a very good approximation of sine of x, which we want to learn. And now in the opposite case, if we have a model, so let me again put some data in here around sine of x. Okay, now if our model has very low degree, like if m is equal to 1, means that our model is linear, we will end up with something probably like this, maybe, or this. Okay, and again, this is not very good approximation of sine of x. In this case, we will have underfitting. It means that the complexity of our model is too low. In other words, our model is too simple to feed to our training data. Okay, so the opposite side of overfitting is underfitting. And we saw that there is an optimal degree. Maybe it is like, I don't know, maybe it was 5 or 10. That was something like this. In this case, the error is not 0, but it is a good estimate of the sign of x, and we want to be able to obtain this model. Okay, now we saw that one way to reduce the complexity of model and prevent the overfitting is using regularization method. And one way is for regularization the model is to use some kind of regularization in the cost function. We saw that, for example, this is the least square term, and we added another term as regularization for our model. In this case, we know that if we increase the lambda, means that with the increase of w's, the cost function will increase. So we want to actually have lower values of w to have lower values of e. In other words, means that if this is the space of the parameters like this, we prefer to be near the origin instead of being here, for example. So if this term, this is the actual cost function of error of our training data, in here and here are the same, we prefer this one, because this term, which is lambda w1 squared plus w2 squared, is has lower value in this case when we are near the origin in comparison with this one. So the regularization actually is one of the ways to control the complexity of the model, and we control the complexity of model with the parameter of lambda. Okay, in this case we just have lambda, but in more complex models maybe we have another ways to regularize the model. We will see that in neural networks or in mixture of distributions, when we want to fit some mixture of distributions, we have some other parameters that can control the complexity of the model. So actually, what do we need again to just to know the main purpose of our goal? We need to determine that some parameters that can perform well on the test data. So how should we determine the lambda or other parameters? We call them actually hyperparameters, because when we set lambda, we train the model actually and learn W after setting the lambdas. These are the parameters of the model, and we call the lambdas or other parameters which we tune outside the model, outside the training of model, hyperparameters. So, for example, in the polynomial curve fitting, the degree of polynomial is hyperparameter, or the lambda is hyperparameter, as you probably guess. So we want to find a model that has the best performance on test data. In other words, on new data, because we see that maybe we have a model that has very good performance on training data, but it is not very good on test data. Okay, like in this example, if we have a new test data in here and we want to estimate our output, the model predicts here, but we know that the true thing in here and this distance is very very high, so the error for the test data is too much. So we want to find a model, in other words, we want to find the hyperparameters such that we have the best performance on the test data. Okay, in other words, we want to prevent overfitting and also underfitting. We want to just find the proper model for our training data. One simple way is to just keep some data for tuning these parameters. What does it mean? It means that if we have all the training data, we split that into training data, maybe 70 or 80% of that for training data, and then we have validation data, which is 30 or 20% of the data. So in this case, we treat the validation data as new data for our model to tune the lambda or m in that case, in the polynomial curve fitting example. So with 70% of the data, we tune the model parameters, which is W, and then after that we test our model on validation data, and based on and we run this with different configuration for lambda and m. For example, for one time we set lambda is equal to 0 and m equal to 5, then maybe we set lambda is equal to 1, m equal to 6, then something like that. Then we test our model on validation data, and then select the model that has the lowest validation error. So this gives us the lambda is equal to 1 and m equal to 6 as tuned hyperparameters. But sometimes, because we do this iteratively, maybe we overfit on the validation data, because we are tuning hyperparameters with validation data to prevent and to make sure that we are not overfit on we do not overfit on on our data, we sometimes have another set which we call test set for final prediction of our model. So if this is our data, typically we divided it by 3 portions, maybe 70%, 20%, and 10%. 10% for test, 20% for validation, and 70% for training. In this case, we just separate the validation data from our data, and we will not use the validation data to tune the parameters of the model. We call this method holdout method because we separate some data for validation of our model and we do not use them as the training data. But if we have if our data is not so rich, or we do not have very plentiful data set, we cannot put just 70% for training because we do not have enough data for splitting it. And so if we have very small data set or small data set and put 20% for validation, this will be so small, and then when we have a very small validation data set, then our error is so noisy and biased, and so this is not good. Okay, how to prevent this? One solution for this is that it's called k-fold cross validation. We want to estimate the validation error. For this, we have the training, we have the data, then we split the data into k-fold. 1, 2, and k different fold. Then we train our model first on these portions and take this as validation. After that, we calculate the validation error on this validation dataset. After that, again, we have these folds. In this case, at this time, we use this one, and this one for training, and use k-1 for validation. And we use all of other ones for training. And again, calculate the validation error. And we continue this process until, let's say this is k, this is k-1, until we set this as validation. And again, we train our model and get E1 validation. Then for estimating the validation error, we just use the average over all of these errors. So this is the validation error. But as you probably find out, the major drawback of this method is that we should train our model in this case for k times, and this could be very computationally expensive. because in holdout method we just train our model one time and use this portion, for example, for training, and use this for validation, and just in one time we obtain the validation error. But in here we train it. This is our first time for training the network, this is the second time, this is the kth time. So in general and in total we trained our model for k different times. And so especially when our model is so complex and hard to train, like in deep learning models, training the model is quite computationally expensive. Maybe you need 2 days for training your model, and in this case if you use 5-fold cross-validation you will need maybe something like 10 days or something like that, or 9 days to just get the validation error of your model, which is not quite good. So when your model is quite large, or in deep learning in general, maybe this k-fold cross-validation is not used, especially when we have very large data set, and the holdout method is preferred when our validation data is rich enough, or our model is so complex. And so until now we learned how to select our model. So this was model selection. Okay, now we want to talk about cares of dimensionality. Dimensionality. What's that and what does it mean? Cares of dimensionality. In curve fitting polynomial example, we had just only one feature, and that was x, and in other words, our example was 1D example. But in pattern recognition or machine learning real world examples, we have very high dimensional data, like images. When you have image, the image could be quite small, even it could be 100 times 100, which is a very small image. Then you will have your feature vector will be 100 times 100, means that you are in 10 to power 4 dimensional data instead of 1 dimensional data. So it is quite high to be to train your model in this space. We will see that training the model in high dimensional data is quite challenging and hard sometimes. The question maybe you ask yourself, okay, why it is bad to have very high dimensional data? It is not actually related to the computational complexity of the model. Maybe it is a matter when you have very quite large number of feature vector. Maybe you need lots of computational operations to training your model, but in here we don't talk about the computational complexity of your model. We talk about the algorithm itself. The performance of the machine learning model will probably reduce, and when you have a very when you have very large number of features. Maybe sometimes it is counterintuitive. As a simple example, let's say you have you want to predict price of house based on area, location. Okay, let's say you so in this case you have two features. So you have two-dimensional space, okay, your feature, because you have two features. So your data will be in this space. Now let's say in this case you get performance of, I don't know, maybe because this is regression problem, like you get the least square error of 10, okay, then on the validation dataset. Now you tell yourself, okay, maybe if I put some extra information for my model, maybe we do better, and we be able to train our model more generally, and so maybe this is beneficial for the model. And you increase the features and add some extra features, like maybe area, square, or number of rooms, maybe. And maybe so just be careful, I say that maybe in this case your performance decreased and you get higher number of test error, and then you will tell yourself, okay, why I increased the information, but now I have lower performance on test data. Now we want to explain why this can happen. Let's say we have a very simple case, okay, and in this case we have two class problem. One class is circle one, another is the X class. Now we want to classify our test data, the new data that will come. One very simple way to classify the test data is to just discrete our space and divide our space into some cells. Then okay, these are supposed to be equal anyway. Now let's say we have new test data in here, which we don't know it is belong to X ones or O class. To determine whether it is belong to the O class or X class, maybe a simple way is to just count the number of instances in this cell. Okay, so in this case we have just one sample from this class and 0 sample from X class, so our test data belongs to O, to this class. Okay, now if we increase our dimension, so in this case you will see that for new data we should have some training data in the cells. Okay, if we increase our dimension, so if we, let's say we add another dimension, another feature to our space, we will need, for the same performance, we will need to increase the number of training data exponentially to get the same performance. Maybe it is better to show the figure from the book. Now you will see that in this case, this is the one-dimensional case. In this case, you increase the number of cells by a square factor. In this case, you will have just 1, 2, and 3 cells. In this case, you will have 9 cells, which is 3 squared. Okay, and in this case, you will have 3 to power 3. Okay, means that you will have 27 cells. Okay, so when we increase our features, we need to exponentially increase the number of training data to training our models. Actually, this is one reason that we want to learn more sophisticated algorithms than this one in here. In here, we had a very simple algorithm that we divided, we discretized the all the space into different cells, and then tell okay, count the training data in each cell, then for our testing data compare these two, and then specify the output class based on the number of each class training data instances in the cells. So this is actually one reason, is that we will learn how to reduce the feature dimensions, and sometimes we want to have feature reduction step. For example, in the case of 2D, when we have something like this, maybe it is better to, in this case we have 2-dimensional features, so our training data, each training samples has 2D is a 2D vector. Now, but it seems that they are lying on some kind of manifold in the space. If we project our data on this line, let's say we find this line somehow and project the data on this line, then we can convert our data into some new features, which is a linear combination of x1 and x2. And when we project our data on that, we have something like this. As I explained, when we have less number of features and decrease the dimension of the data, we can train our model easily, more easily in comparison when we have high dimension data. So in this case, we will get this classifier, which is probably doing very well on the test data. But you should know that this is not always the case, and maybe sometimes reducing the features or feature reduction ruin your performance. So it is just a possibility that sometimes we use feature reduction, and this is that one reason is that I told you we should use data visualization to know that whether we should use feature reduction or not, because maybe sometimes feature reduction decrease the performance of your machine learning model. Maybe you ask yourself, okay, how should we find this line to project the data into this? We call this method as PCA. We will see that in feature reduction methods, and we will learn that. But for now, in summary, I just hope that you learned about model selection, about k-fold cross-validation, which is very important to know because we will use that very often when we use scikit-learn. Even if you want to train your model on iris dataset, which we trained an SVM model on iris dataset last session, you could use k-fold cross-validation to have an unbiased validation error to tune your hyperparameters. So, and the second one was holdout method, which we separate the data into different portions for training data and validation data and test set. Okay, and this our second discussion was about curse of dimensionality, which we learned that with increasing number of features is not always very good, and in fact when we increase the number of dimensions, we need to exponentially increase number of training data in order to have proper model training. Yeah, this is just two things that I hope you learned in this session, and these are so important to have the intuitive into the data science problems, and these are two very prevalent thing in a normal thing in machine learning basics. So hope to see you in the next session. Bye.